It's been called the deadliest piece of equipment Toyota has ever produced. Today in the garage, we're looking at lower ball joints on my brand new 25-year-old Toyota 4Runner. If you're comfortable working on your own suspension and just need an overview you can reference, I'm about to save you 15 minutes of video. There are four 14mm bolts holding the lower ball joint onto the spindle. You can see those here. There's one 24mm castle nut holding it onto the control arm, and one 19mm nut holding on the tie rod end. Once you're ready to reinstall, these are the torque values you're going to use for the hardware. This video was done using the green Toyota flange bolts. If you will be using the black or red, those torque values will be on screen now. Feel free to pause and take a screen cap here if that's all you need for reference. And if you're ready for the parts list, you can skip forward to the timestamp. So let's take a look for a second at the ball joint itself. Here we are under the car looking at an image of the ball joint before we start the replacement. You can see there's a spindle which houses the hub and the wheel here, and a control arm which connects the strut to the frame here. They are connected by a ball joint, an attachment similar to your shoulder that allows you both up and down as well as side-to-side movement. This suspension orientation is pretty typical for a lot of Toyota cars and trucks of this era using a double wishbone suspension. However, this particular lower ball joint connection design itself many consider to be flawed. And that's because the way it's held together is under tension instead of compression. That means when the suspension is experiencing a load, the road force on the tires and the weight of the vehicle are actually pulling the ball out of its socket. This is in contrast to a lot of designs where you see the ball joint is inverted and under compression, like in this instance. Here, the weight of the vehicle and the road force on the tire is actually pushing the ball into the socket. So is a tension-loaded ball joint less robust than a compression one? Arguably, yes. But is the design flawed and its failure mode always catastrophic and unforeseeable? Well, not really. The truth is, the factory part is precision machined and very well made. There are many examples, the one pictured included, going almost 250,000 miles before showing any signs of wear. For their part, Toyota does recommend an inspection every 15,000 miles of the suspension as part of general maintenance. The expected lifespan of a lower ball joint is around 100,000 miles. I was fortunate last month when I was able to purchase this one-owner 249,000 mile vehicle by someone who took very good care of it. Most of the service was done through Toyota, and it was very well documented. You can see in this photo we have some grease leaking out of the bottom of the boot, which was not a major concern in and of itself because the boot was intact. And when we put a dial indicator on it, there was less than 20 thousandths of play. We did, however, notice a squeak when we articulated the passenger wheel from side to side, which is ultimately what moved us to replace the ball joint. And that brings us to the premise of our video. If you're lucky, a ball joint failure at a very low speed turn will result in what could be an expensive repair. In a high speed situation, it could cost you your life. The internet is awash with examples of Sequoias, Tacomas, and 4Runners that have had this particular catastrophe. Thankfully, most of the ones we get reports on are very low speeds and everyone walks away. But it does make you wonder, how many don't get reported and why? If you're over the 100,000 mile life expectancy of your ball joint, or you have some as of yet undiagnosed suspension popping and creaking, it's well worth jacking up your car and checking these parts. And if you don't have that much mileage and your car drives normally, it's still good practice to spend 1 or 2 minutes every oil change just to make sure they're okay. In addition to a metric set of sockets, a ratchet, and a torque wrench, you're going to need 8 bolts to attach the lower ball joint to the spindle. There are a myriad of options here, both from the factory and aftermarket, that will do the job. The reason we went with this particular bolt was primarily price and availability. There's an excellent data set on the forums that outline many of the options available. I'll link it in the description. You'll need a left and a right ball joint. Again, there are options, but it seems like OEM is the way to go. In my situation, after 249,000 miles, my driver's side ball joint had virtually no play, articulated smoothly, and its rubber boot was intact. None of the aftermarket options seem to have a reputation of that kind of build quality. A pitman arm and tie rod puller will be very useful. They're not necessary, but can be borrowed from most auto parts store for a deposit that they will refund when you return the tools. I'll link the model number for these two in the description as well. You're also going to want a thread locking compound. For this install, we've used Thread Locker 242. This is not an oil present application, but if you have some unexpired 243 on the shelf, that will work as well. There's a lot of debate as to whether using a thread locking compound will require reducing the torque value needed for assembly, and we'll get to that as we get closer to that part of the video. And finally, we're going to need 2 additional cotter pins to replace the ones we're taking out of the tie rod ends. So here we are underneath the vehicle. We're obviously underneath because the car is on a lift, but this can be done on the ground if you jack up the front of the car securely. We're going to start by removing these 4 bolts. They're 14 millimeters. And I'm just going to use an impact to zip these out. A ratchet will work just fine. I'm going to go ahead and take that bolt I dropped in the cart and thread that back in. You may have noticed on the stem there's a casting on these lower ball joints. It shows BR. That's the mold design and the side of the part. So in this instance, B indicates a design from an earlier mold and R for the right hand or passenger side of the car. Next, we're going to hit this cotter pin here. I just have a pair of cutters and I'm going to bend that pin as straight as I can and then use the cutters to try and get a purchase on the head. From there, I can cantilever that out or just pull it out of the stem. A pair of dikes or pliers will work just as well. I prefer the cutters because they come to a sharp point. All right, and there we go. Just gonna zip that off, and I'll thread it back just so that the end of the castle nut is barely proud of the bolt threads so that we can get our puller to align correctly on it. We're gonna do the exact same thing on this tie rod end, and this is a 19 millimeter nut. And this is where our tie rod puller will come in. We can slide that right over the collar onto the tie rod without damaging the boot. And just like before, I'm gonna thread this castle nut down so that it's just proud of the threads. A lot of people like to take that castle nut off and flip them around to thread it back in so that it doesn't slip off or damage the threads when you're putting the puller on. And that works just fine. Now, if you're attempting this without a puller, you can still do it with a hammer by striking right here. It may take a pretty big hammer and a few whacks, but if you're using a hammer, take care that you don't actually hit the boot or the tie rod itself. The whole point is to get it to pop out without damage so it can be reinstalled in the new ball joint. If you're using a puller, you're just going to either use a wrench or in this case a ratchet that indexes with the top of the puller to turn it. And you're going to tighten it until it pushes the stem of the tie rod out of the collar. And it doesn't happen here, but be aware when you're doing this, you may get a loud pop when it finally breaks free. That's normal. Nothing is broken. No cause for alarm if it gives you a little fright. So I'm just going to take this nut and thread it off. I'll pull the tie rod out of the way and thread the castle nut back on so we don't lose it. And now back under the vehicle, we're going to do the exact same thing we just did with the tie rod, but we're going to do it with the ball joint. So I'm going to get this puller on here and make sure my nut is just proud of the bolt threads. All right. And the stem is on the bolt. Now it's out of frame, but this is exactly the same as the last one. I'm just using a ratchet to tighten the puller and it's putting pressure upward on the bolt. And there it goes. Once again, we didn't get a loud pop, but don't be afraid if you do. All right, so I'm gonna have to take this nut off to get the puller out, and that's only because the whole knuckle is higher with the ball joint out of the collar. And we'll set those aside. You're not gonna need this castle nut anymore, so you can toss it. And from here, we're just gonna unthread those 4 14mm bolts that we had previously broken free. These are also gonna be replaced, so you don't need to save these. But it might be worthwhile to compare them to the new ones to see if you had any appreciable stretch. That would have indicated that you either over-torqued it the last time or the bolts were loose and the ball joint itself was hitting the head of the bolt, stretching it out. This is also a good time to take note of what the bolts look like to see if there's a lot of corrosion or rust. And these all look pretty good. Now, I'm in Texas, so salt not a big concern down here. And everything under this vehicle looks like all the hardware is disassembling without much effort. It's also been in Texas for the last 25 years. For those of you with the misfortune of living somewhere else, hopefully it's not too bad. Now, with those 14mm bolts removed, there's actually nothing holding the lower ball joint onto the vehicle anymore. It's just the weight of the knuckle itself keeping it in place. You can push straight up on the A-arm to give you a gap to pull that out. Or if you're on the ground and you don't have the room to grab the top of the suspension, you can stick a floor jack underneath the rotor or spindle and lift that up slightly. Once you get it up high enough, you can just tilt it out of the way and lift the ball joint right off. Now let's take this to the table and we can open this up and compare the two. Now, if you bought the Toyota version of the ball joint, it should come with new hardware. One castle nut and one cotter pin. If you look closely at the ball joints themselves, up at the top you'll see 2 casting marks that we looked at when they were under the car, right there and there. BR on the old version, JR on the new part. You'll also notice that the top of these 2 stems are slightly offset. Use that to help you identify and make sure that you've got the correct side. The stems will be pointing at the front of the vehicle when installed. Okay, we're back at the vehicle now, and what we're going to do is make sure before install that all the mating surfaces are clean. Since there's no real rust or corrosion on here, all I really have to do is clean the grease off. You can take a wire brush or a Brillo pad if you've got a little more buildup, rust, or some pitting that you need to get rid of. This was in pretty good shape, so I just got the grease wiped up and now some brake parts cleaner to get the surface clean again, and we're going to wait for it to dry while I go grab that ball joint. I'm just going to rotate this out of the way so it's kind of in position. Shuffle it out from the spindle so that the stem can go back in the control arm. For me, again, because it's up in the air, I'm just grabbing onto the upper A-arm and lifting the whole spindle. There are 2 dowel pins on the outside from where you're looking at this angle, and those are going to need to line up into the corresponding holes in the spindle. You may need to fiddle with it a bit to get it to line up, but when it does, you should have solid engagement. It could also be helpful to use a jack to provide some upward pressure if you're doing this on the ground. And there it goes. And now we're back at the table and ready to prep our bolts with some Thread Locker 242. Just 2 drops in the area where the threads are going to be engaging is all you need. Thread locking compound is actually an engineering adhesive. Its primary purpose is to increase breakaway torque, or the amount of torque to initiate movement in a previously tightened fastener. See, when an engineer designs a system, they have to spec a bolt with the proper metallurgy to apply enough tightening torque to provide sufficient clamping pressure. We call this information a torque spec. The twisting effort we're applying to the bolt is doing a few things. It's overcoming the friction between the bolt head and the surface it's resting against. It's overcoming the friction of the threads themselves. and it's stretching the bolt to compress the joint. Many people in the automotive world subscribe to the idea that a clean, dry fastener, torqued to spec, is the primary and only necessary means of assembly. And I would agree. Thread locker is a good secondary retention method to increase breakaway torque in applications where vibrations might occur. But it's not a band-aid for an improperly torqued fastener. The main concern of the dry bolt only proponents is that liquid thread locking compound acts as a lubricant before they cure, and requires you to lower the torque spec to prevent overstretching the bolt. And this is a very valid concern. Coefficient of friction in threaded fasteners can certainly affect the result of an applied torque from what you set your torque wrench to for an input value. For example, 100 foot-pounds of force on a bolt can yield 150 foot-pounds of turn bolt clamping. Now, Thread Locker claims that you don't have to adjust the torque spec when using their product, and I can understand why you might be skeptical. Luckily, however, we don't have to take just their word for it. There's been a lot of testing done on this. One of my new favorites is from the guys over at the Torque Test channel. They compiled a list of several different manufacturers that produce thread locking compound and put them through a series of tests to see how they all compare to each other. Out of all the products tested, Loctite was the only product that had a perfect 0% off torque wrench target. So if your intention was to add 100 foot-pounds of twisting force to a bolt, the sensor read 100 foot-pounds. I'll leave a link to their video if you're interested in the full range of tests of thread locking compounds. Check them out for excellent, unbiased, and empirical data-driven tool reviews. Now, I don't know what chemical wizardry Loctite did to achieve this result, but it's pretty well documented from multiple sources at this point. If you still have concerns about using thread locking compound, it's certainly not necessary for the install, but it's very cheap insurance. Now, with the 4 bolts hand threaded, we can go ahead and grab our new castle nut and thread that one on as well. Then we're going to grab this tie rod end, stick it through the new ball joint, and then thread the old castle nut on. Now we're ready to come back with our torque wrench, and we're going to torque these 4 in a cross pattern at 59 foot-pounds. Coming up to the 19 now, and this is going to come in at 67 foot-pounds. Now, in these castle nuts, there will be a hole in the stem, so you'll need to use a wrench or your ratchet to continue to over-tighten the nut until you can stick a cotter pin through that hole. And here I've got the cotter pin in. And I'm just grabbing some cutters to hold the end of this cotter pin and bend it over. You can bend it over the top, around the sides, whichever one is fine for you. If you bend it over the top though, you will likely need to use some cutters to trim the excess pieces. And finally, we can hit this 24 castle nut. After you tighten it by hand, you're going to set your torque wrench to 103 foot-pounds. And just like last time, I had to rotate this just a little bit more to get the cotter pin through. I am bending it over, trimming the end, and pushing them all flat to 90 degrees. And that's it, the ball joint is defeated. If you made it this far, thanks for sticking around. This was my first attempt at a video, and it turned out to be a lot more work than I was expecting. If this video helped you out, give it a thumbs up and consider subscribing. I've got more DIYs coming. Got questions or your own tips? Drop them in the comments below, and I'll see you guys next time in the garage.